to go here. Okay, so we'll start with measurements. And when you take a measurement, it is really important to include units. So units are really, really important. And that's because when you have just a number like 100, for example, and if I just write 100, who knows really what that means, right? So if I had 100 pennies, that is something very different than if I had $100. And that's something very different than it's 100 degrees outside, which it seems every day. It seems to be 100 degrees outside lately. So the unit is super important when you're taking measurements. So a measurement should always have a number, and it should always have a unit. And it just gives the number really a frame of reference for what you are talking about. So, if this was 100 pennies, I would be sad. Maybe I'm not. I still have 100 pennies and stuff. But it does give us an idea of what it is. In terms of units, there's really two major types of units that there are. There are English units, which we kind of use here in the US. And pretty much everybody else there uses the metric system. And it can be a little complicated over the years, especially when everybody's sort of doing business with each other, that there could be some mistakes if somebody's using the English scale and somebody's using the metric scale. So like in 1960, they got together and decided, kind of for science and in chemistry, you'll sometimes see it, they came up with what is sometimes referred to as the SI units. And the SI units is basically the International System of Units. Truth be told, it really is the metric system. Pretty much, it's really based off of the metric system. So sometimes in chemistry, and I know Timberlake, who writes the books and stuff like that, likes to talk about SI units and stuff like that, I think so. The SI units sometimes will come up a lot. When we talk about units, it's really important to understand what the unit represents. So when we talk about something like, for example, a liter, that is a unit of volume. When we talk about something like a meter, that is a unit that represents a length. Seconds is usually the units that we see representing time. Kelvin is actually the unit that we see represent temperature a lot in chemistry. And, something like perhaps a kilogram are the units that represent something as a unit of mass. So when you say, hey, my mass was 50 milliliters, that is incorrect, because a milliliter is a volume, and you can't have a mass that's a volume. So want to make sure that you do have an understanding of the units that sort of go with what you're talking about. Is it a volume, a mass? Is it a length, and so forth? Obviously, we use prefixes a lot of times with metric units to sort of change it, like kilogram, kilogram. And the base unit would be a gram. And there are 1,000 grams in 1 kilogram. So 1 kilogram, for example, is 1,000 grams. So those are some relationships. The base unit, again, on that one there is grams. And kilo is the prefix unit. Sometimes you'll see prefixes like kilo, centi, milli, and so forth. You'll sometimes see a table, and there's a table in your book as well, that this says like, hey, kilo is 10 to the 3, right? And it is very common when somebody sees something like kilo is 10 to the 3, I'll write it up here, kilo is 10 to the 3, that when they go to try to use something like that, first off, 10 to the 3 is really scientific notation for 1 times 10 to the 3 is basically what that means. It's basically 1,000 is basically what that means. So it's very common. People always get this sort of conversion backwards. So for example, people oftentimes will go, hey, there's 10 to the 3 kilograms in 1 gram. And that's actually backwards. So when you see a chart like this where it says kilo is 10 to the 3, that's how much there is in the base unit to one prefix unit. So what that means is when we're talking about kilograms and grams, the base unit is grams, right? And the prefix unit is kilograms, which means in 1 kilogram, there is 10 to the 3 grams. So that is a super common thing. People always go to that table and flip those things backwards. So when you pull those things off that table, our centi is 10 to the minus 2. That would mean there is 1 centigram is 10 to the minus 2 grams. So it's always the base unit that gets that number, and it's always one of the prefix units. Questions on that there? So when we use these units, we do change it using these prefixes. But let's talk more about right now sort of measurements and how to take proper measurements. So when you take a measurement, it is really important to always look at the piece of equipment that you're using so that you could take the proper measurement. No matter what happens when you take a measurement, there is always some sort of estimation that occurs. There's always some sort of uncertainty. There's some sort of, I gotta make a guess of what I'm looking at. The degree to which you can estimate is really based on the equipment that you're using. So for example, if we looked at, say, a ruler, and we had so we got a nice ruler here, fairly straight, not bad. Earlier today, my ruler was like scribbly all around. And let's say we wanted to measure something. So let's say we wanted to measure like something like this. The first thing you should always do when you're using a piece of equipment is you should always look at the scale. And you usually will see 2 types of numbers. You will see our markings, really. You'll see larger markings or bigger markings, and you'll see smaller markings on the piece of equipment. In this case, sort of the bigger markings or larger markings is basically 1 centimeter, 2 centimeters is basically what you see. So the difference between the 2 biggest markings there represents how many centimeters total? It is a 1 centimeter difference, right? Between 1 centimeter and 2 centimeters, right? The difference there is basically 1 centimeter. Now, what we want to do is also try to figure out what the smaller marks basically represent when we look at it. And to do that, what we want to do really is sort of count up how many smaller markings there are. And when we go to count the smaller markings, we always do it this way. We actually start at the smallest marking past the big mark. So the big mark here is 1. So we would start counting our first small mark right there. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. And we do stop at the next biggest marking. So that's typically how you count your little markings. Start past the first big marking, stop at the next big marking as you go through it. So there are basically 10 smaller marks, and the total difference between the 2 big marks is 1 centimeter. That means that each smaller marking is how much of a centimeter? Each smaller marking here represents basically 0.1 centimeters. And you could get that by taking 1 divided by 10, basically. Yeah, 1 is the big difference. 10 is how many markings there are, right? Each of the little markings here represents 1 centimeter, which means this first line here would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2 when we get there to the end. Any questions on that so far? At this point, when you take a measurement, there should always be certain numbers that, frankly, no matter who takes a look at it, everybody should agree. So everybody, hopefully, when you look at this drawing here, should agree that my little line ends at least 1.4, right? It's not really exactly at 1.5, so it's definitely, though, past 1.4. So the first thing that you should do with a measurement is always record the numbers that pretty much everybody could agree upon. They're sometimes referred to as certain numbers. So we would record in this case 1.4. These are, again, what are sometimes referred to as our certain numbers. But now when we look at my line, right, it's not exactly at 1.4. It's not exactly at 1.5. And this is where we could have some disagreement among us as to where that line may end. Now, I may look at it and go, I think that's fairly close to being like dead center between those two numbers. And I may record it as a 5. And obviously, again, we would include our units, right, to make sure we got all that good stuff. Somebody else may look at it and go, I don't think it's really quite there to 5 or halfway through. Maybe it's a little before half, and maybe somebody else might record it as a 4. Or somebody else may look at it and go, I think it's a little past the halfway point there, so maybe I'll record it as a 7 at the end. So that is where there is a little bit of disagreement depending on who is sort of looking at the actual measurement. And that is basically what we referred to as our uncertain number, or the estimated number. And it is sometimes referred to as the first uncertain number. And when you take a measurement properly, you should always record all of the certain numbers plus the first uncertain number, the number where there is like a estimate that has to occur. And when you do that, that technically is what significant figures are. Which means that my measurement here of 1.45 centimeters would have how many significant figures? It would have 3 significant figures. Where the estimated digit or the uncertain digit would be which number? It would be the 5. And basically what that is telling you is, well, I think it's like 1.45, but maybe it's like 1.46, maybe it's 1.44, but it's somewhere in that last digit that I recorded there. That is really where the error in our measurement lies. And if you look at the diagram where I drew my line, that's pretty accurate. You know, maybe it's about half, but maybe it's a little short, maybe it's a little bit more, but that's definitely where that error basically lies. Any questions on that there? Now, you do want to look at the scale because scales can change. And let's say we had this situation here. Ran out of screen. We'll try that again. I'll move my number down. All right, let's see that. We'll do that up here. And let's say a little graduated cylinder action going on there. And let's put some liquid in there. And by the way, when you do put a liquid into like a glass container, you typically will see this curvature of the liquid. I'll exaggerate it here. And that is what is known as a meniscus. And basically what happens when you put that liquid into that glass container is the liquid actually is more attracted to the walls of the container than it is with itself. So what ends up happening, the liquid that's in contact on the sides are much more attracted to the sides, so it starts to rise up the sides, and it causes that curvature of the actual liquid that's in there. And when we have a meniscus, and sometimes it's easy to see, sometimes it's not so easy to see, especially if you have a really big sort of diameter, the meniscus gets pretty bad. We always read from the bottom of the meniscus. And that is because that is really where the true volume is. They're rising on the side is sort of artificially. It's not really where the volume is. It's just because of the attractive forces. The actual volume is where it's sort of in the middle. Because in the middle, it can't really touch the sides. So it stays exactly where it's supposed to be. The sides touch and they kind of come up and curve that liquid. So when you have a liquid in there, you do want to always read from the bottom of the meniscus. So we do want to approach this the same way when we look at something like this, and we'll call these milliliters here. We want to look at our big scale here. So the difference on the big markings is we have 10 and then we also have 20. So the difference between 10 and 20 is how many milliliters in this case? 10 milliliter difference, right? So there's a 10 milliliter difference between 10 and 20. We also want to look and see our smaller markings, what we got going on there. So counting at the first smaller marking past the big one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Again, stopping at the next big number there. So once again, here we have 10 markings where the total difference is 10 milliliters. That means each smaller marking is how much? It is 1 milliliter, right? 10 milliliters divided by 10 is 1 milliliter each. So if we look at our meniscus where our liquid is curving, we're somewhere over here. And if we did our numbers here, each one is 1 milliliter. That means this guy would be 11, 12, 13, 14, 15, maybe. There we go. 16, 17, 18, and obviously 19 there. Everybody would agree that it is at least my really badly drawn 15 there. So we would want to record 15. In this particular case, our meniscus is about there, so maybe it doesn't look half to you at this point. So maybe it's like 15.3 milliliters. This again would be all my certain numbers. This would be my first uncertain number, right? Which is what we want to record. And this would be the proper reading here. This would have how many significant figures then? It would have 3 significant figures, where the uncertainty here does lie in that third number there, the 3 basically. And that would be the proper way to do it. So again, here we do have the same sort of 10 divisions, but because the scale is different, it gives us a different number. Typically speaking, when you take a measurement, you typically can go one more place to the right of the smallest marking. So in this case, the smallest marking was the first decimal place, right? We could go one more to the right, which is what we did to take our reading. If we look at the graduated cylinder here, our smallest marking was 1 milliliter. We could go one more place to the right, which is what we did here, right? To the first decimal place. So in general, we could go one more place to the right of the smallest marking. Not 100% of the time, but probably 99% of the time, you could go one more place to the right of that smallest marking. Question on that? An example of where you maybe couldn't do that would be a situation, say like this. So once again here, we'll just put our right there. Once again here, our big marking is going to be 10 milliliters. Now, when we look at our small markings, there's 1, there's 2, there's 3, there's 4, there's 5 markings in this case. That means that each of the smaller markings in this case represents how much? There are 5 lines and the difference is 10. So if we take 10 divided by 5, you get 2 milliliters. So each of the smallest markings in this case would actually be 2 milliliters. This guy would be 12. That would be 14. That would be 16. That would be 18. And that would be 20 coming up that way. So in this particular case, it actually goes by 2s. So even though the difference there is the exact same difference that we had in the previous one, 10 milliliters difference, right? Because there's different types of markings, they don't represent the same. Yeah. Yeah, so if you want to figure out what each of the smallest markings represents, that's what you would do. You would take the difference between, the two big numbers. There's a lot of big number differences, but basically it should be the same difference between each of the two big numbers. And you would divide it by the total number of markings, that smaller markings that you have. Yeah. So that's how we got to 2 in this case. Again, the big difference was 10 milliliters and there was 5 markings, right? Which means that 10 divided by 2 gets you to the 2 milliliters. And that was the same thing as basically we did over here. There was a 10 milliliter difference and there was 10 markings, right? Which means each one was basically 1 milliliter. And over here, there was 1 centimeter difference and there was 10 markings and that gave us the 0.1. So that's how you can figure out how much each one is. Now, when we look at where our sort of meniscus is, it's actually between 14 and 16. And what number is between 14 and 16? It is 15, right? So in this particular case, because of the way the markings are, the best you could do is record 15 milliliters. This would then have how many significant figures? 2 significant figures. And if this number has 2 significant figures, which one would be the estimated digit or the uncertain digit? It would be the 5. Yeah, the 5 is our uncertain number because could be 16, could be 14. The problem here is because of the scaling, there's not enough room in here between those two numbers, or there's 2 dashes to figure out kind of like where 14 ends and 15 begins. There's just not enough room to sort of figure that out. So that's why we can only obviously go to the whole number. That means that the uncertainty here lies in actually the 5. And again, it means basically it could be 16, could be 14, which is, somewhere in that ballpark is really where the error is. Is that a really good measurement? Not as good as perhaps the one before, because our uncertainty before was actually over here, right? This basically means it could be like 15.4 or 15.1, right? So the error and the imprecise in our measurement is actually in the first decimal place, right? Which is a lot smaller of a difference than like it's 15, 16, or 14, right? That's a much bigger sort of difference between it. So it's really important. That's why it's really important to record all the numbers correctly to the right number of digits, because if you lop off a digit, you actually make your measurement pretty much crappier than it should be. So it's really important to do that. Question on that? So you asked about how to figure out the smallest marking. You could also figure out how far you could typically take the reading by taking the smallest marking and dividing by 2. And it will tell you basically how far you could take that reading. So for example, on this one, our smallest marking was 2 milliliters divided by 2 means I could take my reading to basically 1 milliliter, which is what we did. On this one, the smallest marking was 1 milliliter divided by 2 and you get 0.5, which means I could take it to the first decimal place, which is what I did in that particular case. So you can actually take the smallest marking divided by 2, and it'll actually tell you how far over you could actually take the reading to properly. And that is what we see here. Smallest marking is 0.1 divided by 2 gives you 0.5, means I could go to the second decimal place to take my reading. And or you could just remember one more place to the right is usually what it is in most cases. Speaking of sort of making a measurement worse than it should be, so for example, let's look at our ruler here. And we'll go like dead on there. So this is basically the same setup as we had on the first ruler. The big markings here is 1 centimeter. The smaller marking, there is again 10 smaller markings between them. That's going to give us our 0.1 centimeters. So this would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. So when we look at this reading and we're going to go, this is like dead on that number right there. What should we record in this case? Should we record 1.5 centimeters, 1.50 centimeters, 1.50000 centimeters? Because more zeros makes it look a lot more scientific, I think, right? It doesn't really, by the way. All right, which one, or is there a difference in those two numbers? Is there really a difference in those two numbers? So I see some people say no, and it's a very common thing that when people do a lab like you're going to do on Monday, they will record 1.5 and go, it's on 1.5. So probably because maybe they're not sure how to take a proper reading, when they go, I definitely see 1.5 sitting there. So that seems like a very safe answer. So let's think about it in terms of the different types of measurements here. Let's start with the 1.5. If I had 1.5, that would have how many significant figures? 2 sig figs. That means that the uncertain number would be which number? It would be the 5. So basically what you're saying in this is, I think the measurement is 1.5 centimeters, but maybe it's 1.6, or maybe it's as low as like 1.4, right? The error's there in that last number, basically. And if we look at the actual line, we see that it really is like nowhere near either of those numbers, right? It's not even near there. So not the greatest measurement. Let's take a look at this one here. This measurement would have how many significant figures? It would have 3 significant figures. The uncertain number would be the 0 here. And that means that looking at that, we're saying, I think it's 1.50 centimeters, but maybe it's 1.51, maybe it's 1.49. Now that little difference, right, really does agree with what we are actually seeing on this particular scale, right? It's like right on that number, which means maybe it's just a hair short of that number, or maybe it's a little bit above that number, but that is really what we see. So because we can, with this particular ruler, take it to the second decimal place, we do want to record it as 1.50. That is the correct measurement. It's actually a much better measurement than this measurement, right? This measurement has a lot of error built in there, right? There's a big span between 1.6, 1.4, and 1.5. So we would not want to do that. You would want to record it like on the right there. And it's a common thing that happens with people when they measure things. They go, it's right on the number. I'm just going to record the number that I see, which makes sense. But you do got to still look at the scale. And if you have the ability on that piece of equipment to actually take it, like in this case, to the second decimal place, you do need to put the 0 in there to maintain the proper reading, the proper number of significant figures, and frankly, not screwing up your measurement and making it a much worse measurement than it should be. So if we lopped off the number, although it doesn't seem like there would be a big difference, you would actually be making it a very bad measurement rather than what it should be, a pretty good measurement actually over there on the right hand side. Question on that there. So speaking of sig figs, when we talk about sig figs, there are some rules to counting significant figures. The first rule is any non-zero is significant. So any number that is non-zero is a significant figure. So if you had 3, 2, 5, 6, when we start counting significant figures, it is always left to right. So we go left and we start counting as soon as we hit the very first non-zero, which would be the 3 in this case. The 2, the 5, and the 6 are also non-zeros. That would be 4 significant figures for this particular number. They would all be significant. Now, zeros is really what gives people trouble. There are 3 different types of zeros. There are leading zeros. And those are all the zeros that come before the very first non-zero number. And they are not significant. So for example, 0.000453. Starting left to right, these are all zeros, placeholders, if you will. We don't start counting until we hit that very first non-zero number, which would be 4. And then the 5 and the 3 are also non-zeros, so those would be significant. So this guy here would have 3 significant figures. Question on that there. Now, sometimes people ask, well, you know, the zeros there after a decimal point, they're not significant because we haven't hit the very first not significant figure yet. So we have to hit that first significant figure to kind of start counting everything. There are zeros that are sometimes referred to as trapped zeros, captive zeros. Those are significant. Those are zeros that are between 2 non-zeros, like 4004. We would start counting here, so that would be significant. These zeros here would be trapped, so they would be significant as well. And our 4 at the end would also be significant, so that would be 4 significant figures. And lastly, the zeros at the end, which are sometimes referred to as trailing zeros. Those may or may not be significant. What determines whether or not they are significant is there a decimal place? Decimal place, not really decimal place, decimal point, I guess is a better way of wording it. Is there a decimal point in the number? If there is a decimal point anywhere in the number, it doesn't have to be near the zeros. It will make those zeros at the end significant. If there's no decimal point written, then all the zeros at the end are not significant. So to give you an example of that, 12,000 like this has only 2 significant figures. We start counting here. That is 1. That is 2. These are zeros at the end. There's no decimal point written. If this was a measurement, they are not going to be significant. This guy would have 2 significant figures. If I wrote 1.2000, this would now have significant, significant. All 3 of those zeros would now become significant because there is a decimal point in the number, and that would be 5 significant figures. Once again, the decimal point does not need to be near those zeros. They just need to be in the number. Question on that. If I had 0.00100200, how many significant figures would that have if that was, say, a measurement? Not sure how you get that measurement, but how many significant figures would this guy have? It's a good question. I just was writing numbers. I'm not sure. So let's see. All these zeros here are not significant because we have not hit the first significant figure yet. We would start counting right here at number 1. These zeros would be significant because they're trapped. The 2 would be significant because it's a non-zero. And now the question is, are the zeros at the end here significant? And the answer is they are, once again, because of the decimal point that's there. I lost track. You might be right there. 1, 2, 3, 4, 5, and 6 significant figures which would technically be all those I just circled, would be the significant figures. Question on that. All right, last thing to leave you with here is when you're trying to identify the estimated digit or the uncertain number in a measurement, it is always the last significant figure, not the last number written. Now, sometimes they are the last number written, and a lot of times they are the last number written, but it is really the last significant figure that is written. And what I mean by that is if I asked you, what is the estimated digit in that top number, which number is it? It is the 2 because there's only 2 significant figures. This would be the last significant figure that's written there, even though there's zeros at the end. The 0 at the ends are important because the value here is 12,000, not 12, right? There's a big difference between 12,000 and 12, right? In terms of the meaning of it. That means that this measurement is not the greatest measurement because what we're really saying is, I think it's 12,000, but it could be like 13,000, but maybe it's 11,000. That's a pretty big iffy. I think it's maybe somewhere in there, right? That's a big degree of uncertainty in that measurement, right? As opposed to if I took the same 12,000 and laid me up a decimal point right there, how many significant figures would it have? It would have 5. These would be significant. These are technically the last zeros there. Decimal point happens to be behind them. Doesn't matter, still in the number. That means that all these guys would be significant, and this would be 5 significant figures. Now, where would the uncertain number be? It would actually be the last 0, right? Which means this is like, I think it's 12,000, but maybe it's 12,001. Or maybe it's 11,999, which means which one would be a better measurement? It would be the last one there, right? The degree of uncertainty is way over there, right? To the right, as opposed to in the thousands place, it's in like the ones place, right? The uncertainty, so it's a much better measurement. So take home message is make sure you look at the scale and figure out how far you can take the reading and don't lop off numbers, you know? Besides the fact that get marked wrong, don't lop off